Hello, good evening, and a warm welcome to the 5th week of Hillary term at the Oxford University Scientific Society. You may now be dealing with the infamous 5th week Hillary Blues, but don't worry, because in just a few minutes you will forget about all of this with a truly fantastic talk. This week, I have the honor to welcome Professor Alán Aspuru-Guzik as our speaker. Professor Aspuru-Guzik is a professor of chemistry and computer science at the University of Toronto in Canada. Born and raised in Mexico and previously professor of chemistry at Harvard, Alán is an interdisciplinary scientist and a successful serial entrepreneur whose research crosses boundaries, including quantum computing, artificial intelligence, computational chemistry, and more, all orbiting around a single concept: the objective of designing new, better, novel light harvesting materials. Just as a reminder, if any of you have any questions for Professor Aspuru-Guzik, please pop them in the chat and we will read them at the end of the lecture. Without further ado, Professor Aspuru-Guzik, the stage is yours.
So you might have heard that Carlos was an undergraduate in my lab. A pleasure to work with him before. He has a standing offer to become a postdoc in the lab. Pleasure, Carlos. Okay, now let's get started. It's really a pleasure to be here. Last time I was in Oxford. Okay, so assuming people in. So I really think it's a very interesting time. This is a plot. I see it. Sometimes I feel kind of, not really paying attention to big consequences. Think about it. 2021, 22 here, somewhere here, right? And you can see that we need to lower the emissions of CO2 within the next decade to barely make half Celsius warming. I think that's going to happen. I probably will be here. But we need to work together with policymakers, the government, and also scientists to really accelerate the discovery of materials, but also, of course, deploy them and actually have these technologies in market. And what is the problem? I mean, if you really want to think about, from the perspective of chemistry or material science, in impacting any of this, is the fact that if you look at the history of the discoveries of relevant materials and all the way they reach to market, really the numbers are staggering. It's about 25 years, thinking about solar cells or emitting diodes, etc. How can we get from that time scale of, say, of the order of tens of years to a time scale of the order of a year? The main thesis of this talk and the main thesis of what my research lab is trying to achieve is to increase the throughput of all the different steps to just try to get a factor of 10. And it's possible we're getting factors of 2 and 3 here and there. And for that, we want to think about how to accelerate the synthesis, the fabrication, and the testing of materials, okay? In an integrated fashion. You want to think about the entire process of discovery to manufacture as a platform. And you want to think about where you can cut. But also you want to think about the concept of a self-driving laboratory, a laboratory that uses statistics and machine learning to, based on the at least experimental information as it can have, gain the maximum amount of information it can have, right? Rather than the old ideas of doing high-throughput screening where people just ran many experiments and then did the statistics later. We want to do the statistics on the fly and to make decisions about what to do next. So that is the idea of a self-driving laboratory depicted on the right. In my lab, I have been involved in several projects where we were thinking about discovering materials, as Carlos was talking about. One of them was a collaboration with a project led by Roy Gordon and Mike Aziz at Harvard on organic flow batteries. And this is a project where, even though it was fast, it took about 5 years to come up with the first functional molecule that potentially could be in a device. So if you think about the fact that we needed a second molecule for the other side of the battery, it takes us roughly in the same time scale that I was mentioning. So can we do something faster? That has been actually my mantra. So it is like a responsibility, but also a pressure that last year the MIT Technology Review mentioned 10 breakthrough technologies for 2020. And the idea is to think about AI discovered molecules. Here they, of course, emphasize drugs, but also AI discovered materials, molecules for drugs or for materials. Is more or less the same technology. And notice that they say availability 3 to 5 years. And they mention the following institutions. I'm affiliated with robotics, a startup I co-founded, as Carlos was mentioning. My university, the Vector Institute, and also we collaborate with in Silicon Medicine. So I feel involved in this, in the mix of this breakthrough technology, as is mentioned. So why was it mentioned, the breakthrough technology? What are we going on? This is part of this talk. But before that, we're going to start just defining some terms. I know this is an interdisciplinary audience. So at the top, we have our general artificial intelligence that, is like Terminator style. But you can also think about shallow artificial intelligence, which is what the Teslas or the self-driving labs that we're going to be talking about are doing. And within it, deep learning, Bayesian modeling, and robotic process automation are going to be the tools that we're going to be employing. But of course, there's other tools from AI that could potentially be employed as we move along. So what is the big deal, right? Because people for a long time have been doing what is called structure-activity relationships that take representations, say, of molecules, and they handcraft features. For example, what is the energy of a particular orbital? And I've done a lot of this myself, right? Or what is the polarizability of the molecule, or is partition coefficient in nocturnal and water? You come up with certain properties you handcraft, and then you build, in this case, a generalized linear model. Property Y is a function of this weight matrix multiplying this vector, and then this shift, right? This vector X prime. What machine learning does, in a nutshell, is replace that handcrafted feature by means of a lot of data to generalize an optimized or computer-made representation. We're going to call it the Z vector. And this Z vector is going to be perhaps unrecognizable to a human, what exactly was mixed there. But turns out, in general, it's going to be more efficient than humans randomly picking features. And that's kind of the revolution that has allowed a lot of different, machine learning applications, such as computer vision and language recognition, language generation, etc. So my own adventure started, early on when I was at Harvard with David Dubenot, now professor at U of T. Ryan Adams is now used to be a professor at Harvard. He's now a professor at Princeton. Rafa Gomez-Bombarelli is now a professor at MIT. So it was a great cadre of people that David asked us, what did you guys use to learn? And we said, well, what we used to learn is we take this representation that is a fixed length discrete vector that is built by first looking at the atom, then at the nearest neighbor, then the next nearest neighbor, and so on. So advancing and advancing in some sort of hierarchy of a circular atom. That's what it's called, a circular fingerprint. And we just use this technology from the pharma industry. So what David said is, why don't we generalize it? Let's put hidden weight vectors in these different layers of this network. Let's make this real valued instead of discrete valued and make it differentiable. And that started a field. This paper has more than 1,000 citations. It's growing really quickly. A lot of people in machine learning are thinking about graph representation of molecules. And it's been a great adventure, right? So in this paper with Benjamin Sanchez Lengeli, which, by the way, Carlos Ulterial, which introduced me, worked with when he was in my lab, and I, in this paper with Benjamin, we kind of write what was the state of the art a couple of years ago in what I think is the most important concept, which is the representation of a molecule. What is a molecule? Ultimately, you want to think about its full quantum mechanical wave function, but you could also think about it in terms of the fragments. This is not dissimilar to how organic chemists think of molecules, or as a graph, as I mentioned earlier, or potentially more mathematical objects like potentials or Coulomb matrices, or as I will be discussing a lot, text. So it is the choice of that representation, the choice of the model that will make you successful. And let me show you an example. This is one of our old data sets, the Harvard Clean Energy Project. We're trying to predict here how well a molecule will become a solar cell. And notice here the performance of our neural graph fingerprint that I mentioned earlier in MAE and RMSE, okay, compared to simple models like random forest, which are very simple models that people have been using for a long time in machine learning. And you can actually see that most of the models saturate, more or less at the same values, unless somebody, like in this case, Rishi Kondor, comes up with a tensorial representation that thinks about the symmetry of the graphs and actually, in some sense, involves more physics into the problem and ultimately really makes a big gain in terms of the errors of this model, okay? So what this teaches you is that you really want to spend time thinking about the representation of the molecular material. So now let's just talk a little bit about applications. And this is an application that my lab and I have been thinking a lot about over the years, is the application to light emission. In this case, organic light emitting diodes. And this was what motivated us to enter the field of machine learning early on. So it was around 2013 or so, or 2014, where we were approached by Samsung and stood up a collaboration between Harvard and MIT to try to find more molecules that did something very exciting. So for those of you that don't know enough organic photochemistry, the idea is that there are two excited states for molecules, singlets and triplets. Usually the triplets of the organic molecules are very different than the ground state singlets, and therefore do not emit radiatively, but emit non-radiatively, due to the quantum mechanical matrix element of the transition dipole between these two states. You can actually increment the fluorescence of these states by actually, and that basically means that any garden vanilla molecule, if you put it in a device, say a cell phone, will only emit 25% of its energy, because you will have a statistical mixture of the spins as they come out of the electrodes, and therefore 75% of your energy will be trapped in these triplets. But if you actually put a transition metal in the molecule, you can actually have, by spin orbit coupling, this mixing between the singlet and the triplet, allowing phosphorescence from the triplet, and then having higher quantum yields that are possible using just fluorescence emitters. This technology is what is in the pixels of your cell phones today. But the blue pixels have a big problem, because if you put a transition metal, these molecules become unstable. So around 2012, Chihaya Adachi pioneered the idea of trying to find molecules that had the cake and eat it. Raise the triplet energy by lowering the exchange integral between the frontier orbitals of these molecules in such a way that the triplet could actually thermally activate and fluoresce from the singlet. And this is a material that is a very strong candidate to be used in blue molecules, because it does not involve transition metals. At the time, there were very few molecules known that had this effect. And what our goal was to actually use this project to actually generate a library of these molecules, calculate a subset of it, use the machine learning models I just showed you earlier to predict the rest of the library, filter, down select, and make devices. And this is where the bottleneck of materials discovery really shows it, at least to me, because we were able to use machine learning and quantum chemistry in literally 1 million compounds. Okay, but we were only able to synthesize and test, 40 molecules, and out of them, 10% success rate. We had 3 champion candidates that actually made it for a Nature Materials paper, and it's a fantastic story in terms of academia, but it's not a great story in terms of commercialization, because these molecules are not the ones that are on your cell phone. So how can we increase the throughput of this? It's kind of really what keeps me up at night. How can I make this process faster? So you might have heard about the revolution of generative models, and this is an example of a great use of them, generating fake faces. All of these faces are generated by a computer. You might be able to notice that especially the one in the right has a few defects. The finger looks a little bit weird, and there seems to be an ear missing. Nevertheless, the computer generates these faces that, to first instance look like a human, but they come from a non-trivial probability distribution, the distribution of pictures of people. And you can generate from that distribution new samples that can look like people. This is not old idea for science. You might want to recall the Monte Carlo method introduced during the war in the 1940s. To actually simulate the probability distributions of complex processes such as scattering in neutral reactors, or of course the much more known Metropolis Monte Carlo method for sampling from the Boltzmann distribution. These generate samples or copies of a probability distribution, elements from probability distribution, in this case the partition function. Having said so, right, how can you do that for more complicated distributions? And this is one of my favorite papers of my own career, where we actually did that with Rafa, David, and the people, most of the people that I mentioned, plus others like Benjamin and Jennifer Wei, where we actually took a string representation of molecules called SMILES. We'll come back to it later, and did what sounds very weird. We took a machine learning model. These are supposed to represent layers of neural networks. that compresses information in a roughly 200-dimensional latent space. Remember that C vector I was telling you about, and then decompresses it back to its own representation. So if you just forget about the right-hand side here, this is a model that seems to be doing almost something trivial, which is you show it a benzene and it just throws the benzene back. But if you train this model, say, with about 250,000 or so drug-like molecules, you will end up with a space here that is actually continuous differentiable space that's somewhat somehow compressed into a lower dimensionality what is drug-like molecules. So what we did in that paper is actually attach a third model, in this case a Gaussian process, but it could also have been a neural network or whatever model you wanted, to this 200-dimensional latent space, and now have a way of climbing up the ladder in that model and then trying to maximize one property or properties, then down project back to the original latent space, and then back decode what was the molecule that had such a property. This solves a very long-standing problem, the problem of inverse design in material science or chemistry. That's why I'm so happy about this paper. So, of course, there's all sorts of other methods that people have been employing. You can see them listed here. Generative adversarial networks, which I won't discuss very much here, but a little bit mention them, reinforcement learning, etc. So it is this kind of like very complicated landscape of machine learning models that, combined with the representations I told you about, it's really a rich ground for progress. So I'm very proud of having helped as a consultant and collaborator my friend Alex Shaboronkov and his team at In Silico AI. Because in this particular project, in 46 days, an adversarial autoencoder, this technology that we pioneered for chemistry, was employed for real, actually, in the sense that it was employed together with many different filters to predict DDR1 kinase inhibitors. And we collaborated with Wuxi, which are co-authors of this paper, to very rapidly also do cell assays, liver assays, and even live rat assays, all of it within 46 days. And the lead candidates were good enough to publish a Nature Biotechnology paper. Same caveat as I told you before, they are not really treating DDR1 kinase diseases, such as muscular dystrophy. Obviously, there is a huge pipeline of discovery behind this, but it gives you an idea of what the state of the art is in terms of this happening. MIT colleagues had a paper in Cell with antibiotics, and there's a couple other examples where people have actually been able to use AI to discover lead candidates faster and test it experimentally since then. And this is only published in 2019. And we believe this is the reason why MIT, recognized this field. Now, since then, my group has been busy. We've been working with our collaborator, Yusung Yoon, for example, in solids. Here you see low energy potential phases of vanadium oxides at particular compositions that people don't know about, but we believe this could potentially exist as potential new phases of vanadium oxide. They were generated by a generative model. And just appeared this year in Nature Machine Intelligence, this paper, which I consider to be the state of the art in complexity, because this is in between a molecule and a solid, right? It's a periodic material that uses these molecules connected to transition metals. It's called a metal organic framework. And you can think about it as a sponge, okay, where these little circles that you see here represent empty spaces where you could, for example, do catalysis or separate gases. And in this paper, we show that you can use these models to predict the new potential materials for gas separation. This has not, of course, been this has not been realized yet because it's very hard to make these experiments, and this paper just appeared, where it gives you an idea of more or less where we are in terms of applying these generative models. But I will come back to representations here and then discuss, can you make a progress in the representations? I mean, after all, this SMILES representation comes from the 80s. And it's nothing more than a little computer program, right, that says, this is a way to draw a molecule based on its carbon, nitrogen, carbon, in this particular case here. And by the way, I just found out recently the molecule that my postdoc selected for the paper is MDMA, the molecule in ecstasy. So this is the molecule you're looking at. But you can see here how this carbon represents here, and you can continue moving around. Some of the problems in SMILES is that they can have typos. If you omit a parenthesis, the SMILES will be invalid. If you, if these numbers here are pretty problematic because they tell you where to connect these close ranks. So what Mario figured out, inspired by his work on quantum optics, and this talks a lot about multidisciplinarity, is the fact that You could potentially make a smarter program, right? A program that actually contains a better grammar that allows you to encode these numbers in a different way and reorder the atoms in a way that basically the symbols can predict what is the next valid set of symbols that come next, and therefore allows you to have 100% representable representation and no loss. So I argue the controversial thing that there is no reason whatsoever to use SMILES for machine learning anymore. You should use always selfies because the selfies are 100% representable, and you know, therefore we're very proud of having come up with selfies. I mean, for example, here are the two. You remember those are about 200-dimensional vectors. Let's just look at 2 dimensions of them. This is the projection of them in the space around a molecule. And the green means a valid molecule, and the red means invalid. So you can see how most of these models are spending a lot of time trying to just get the grammar right. And the green regions are the ones where the model gets the grammar right, and the rest is going to be garbage that is generated by the model. Whereas on the right-hand side, you can see the selfies is, of course, by construction, 100% representable, which allows you to have about 2 orders of magnitude more molecules in any volume of this latent space. Okay? If you have 2 orders of magnitude more diversity there, obviously your model is going to be much more powerful because the neural network is learning how to do the chemistry that you want, not just how to write the string. So you remove a lot of the stupidity out of the models. Same thing here in the generative adversarial networks. You can also see that they generate much more diverse molecules rather than the baseline of using SMILES. So we're very excited about the selfies and therefore started looking at several applications that actually exploit the fact that they're 100% representable. Advertisement, obviously, there is a code that you can download and install in your computer, pip install selfies. My lab is very big about trying to release codes such as this one. So I really recommend you in a single line. You can go back and forth between SMILES and selfies. And here's a paper, for example, that appeared in the ICLR this year, where we actually take the advantage of the selfies because it's very hard to do a genetic algorithm based on SMILES, because if you try to mutate a SMILE, many of the SMILES that you will mutate will be actually invalid. You could do tricks to fix that, but in this case, what we do is just basically randomly mutate the selfies with interesting mutation operators. And you can see that even just generating random selfies can have a better performance. Here we're trying to maximize the a penalized form of the log P, partition coefficient between octalone and water. And you can see here many generative models from different groups, including ours. Variational autoencoders, generative adversarial networks, recursive neural networks. And even if you just randomly search for selfie space, you will be more efficient in finding the solution. But if you actually use genetic algorithms, in this particular case, our improved genetic algorithm that you can see the details in the paper, you can see that we can get a very, very large penalized log P as compared to the other models. Okay? So this tells you that selfies gives you like a big advantage. And just last December, we put out several papers on the archive. You can see here genetic algorithms. I'll tell you about Stone as well and about Pasithea. So Pasithea is an algorithm about what is called deep dreaming. She's the Greek goddess of hallucination. And actually, why don't we spend some time learning about deep dreaming? We believe our paper is the first application to science of the deep dreaming technology. So let's just look at this video for a while. I know I talk very fast. I'm very excited. So let's just actually deep dream for a little while. Okay, so you're seeing here, for example, a neural network trained on images, and you are navigating through it. Let me try to explain to you what that means in the next slide. But what you're seeing is how the different layers of the network are reacting to a challenge. For example, you tell it, draw me an animal that you have not seen, and so on. And you can see here how if you start looking at what will come out of the representations from different layers of this network, you will see things that start looking like different types of fantastic animals. So really recommend you to get stoned and actually watch this type of video. Okay, let me disconnect. Sorry, disconnect, but let me leave YouTube, go back to this, and continue. So how does this work, guys? You might be like, oh my God, what did Alán show me? Okay, hopefully at least I woke you up. I know it's a little bit late in Oxford. So what you see here is a molecule that is feed-forward trained in, basically forward in a neural network, right? So you take the molecule goes through the weights of the neural network and predicts a log P, partition coefficient between octanol and water. Then you use backpropagation, which is a differentiation technique to try to update the weights of this network, and this is how you train it. That's how you train any type of neural network. What deep dreaming is all about is now you're going to freeze the network as it was trained to predict log P's, and literally you're going to go backwards, okay? What we're going to try to do is fix that log P value. Remember, the weights of this network are fixed. But now we're going to take a representation such as SELFIES that is 100% representable, and we're going to relax it into real valued numbers so that it's differentiable. Okay, so we're going to make the same trick I told you at the very beginning we did for the fingerprints. We're going to do it now for the SELFIES. We're going to relax it into a differentiable space. And now we're going to try to optimize the molecule for a particular log P. So we're running the network backwards, so to speak. So as you run your trainer, what this thing will try to do is try to give you, and every time you run it, because we initialize randomly, you will be getting different results of molecules that could be potentially, that could have that log P, right? Are predicted to have that log P. And this is very similar. It's another inverse design technique, right? So now I just show you a new completely new inverse design technique, which is based on deep dreaming, okay? So remember that I was showing you what the neural network was saying. Well, we wanted to know what happens. And that has to do with what is called interpretability. The problem was trying to understand what the neural network was trying to do. So those of you that are chemists or material scientists know that if you want to make a molecule more soluble in water, you probably want to make it smaller and make it look like water. Obviously, water is 100% soluble in water, but you can make it look like ethanol, okay? Or smaller the better, right? So in this simple model. So basically, if you optimize towards the negative log P, you will end up getting molecules that are shorter. Whereas if you want to optimize this molecule and you want to make it more fatty or less soluble in water, you will extend it, for example, okay? Or you will, for example, add double bonds to make it even more fatty, okay? In this particular case, you're going to remove this ammonia, okay, and actually make it more and more fatty by removing this ammonia and more double and triple bonds. Obviously, these molecules are not very chemically realistic. This is dreaming the same way as those weird animal faces that you saw. But you can see here kind of like the quote-unquote thought process of the processes that this deep dreaming model is learning. So it gives you an idea of what was going on inside the neural network layers. So it's some way of extracting some sort of human conceptual information about what the neural network was thinking. This is a trivial example, but imagine that you want to solve a more complicated problem in chemistry or material science. Doing this deep dreaming exercise might allow you to think about the problem in different ways. So now, I happen to live in Toronto, and I don't know the status of the legality of drugs in the UK, but drugs are legal here at the national level. So you can walk around Toronto, and this is 2 blocks away from my house, and find a place where if you follow them in Instagram, you will get a little card where you can actually get eventually free kush marijuana. So it's not surprising that in Toronto, we named our algorithm Stoned. So we call it super fast transversal optimization, novelty, exploration, and discovery. Okay, and combined with SELFIES, you can imagine taking a selfie stoned. Okay, and what is stoned? Stoned is basically a more complicated version of what I showed you before of GAD, an algorithm that actually modifies the selfie strings with no training whatsoever to have extremely different tasks, such as optimization, novelty, rediscovery, etc. Okay, so this is an example of interpolation. Okay, so what we're trying to do is take a molecule that is good against a particular target. This is the docking score. And another molecule that is good against another particular target. This is its docking score. And see if we can use this algorithm to interpolate between them and find a molecule that jointly has good functionality against both of them. Okay, so looks like molecule 6 could do the job. So this is an example of some interesting drug-like design problem where you could do something interesting by using Stoned. So Stoned, I believe at the moment, is probably one of the best algorithms out there to do this. You can see here this table in our paper that tells you what are the different advantages of using stone versus generative models. And it tells you that one of the biggest advances here was the introduction of the SELFIES that now has us, ahead above other groups that are using still smiles or other more primitive representations. So I strongly recommend you to start thinking about SELFIES and also look at these papers. So now I'm midway through my talk, and this is the right moment to abandon the machine learning world. We'll come back to it in a little while, but come up to a little bit higher level topic. And the topic is, I told you that ultimately my goal, or the goal of many of my collaborators and other people around the world, is to accelerate materials discovery. For that, AI is a piece of it, but you also want to, of course, not forget about the humans, orchestrating software, robotic platforms, databases, and all of them together are what we call materials acceleration platforms. And over the last few years, since we wrote this report in 2018 under the Mission Innovation umbrella, there were many papers where we tried to kind of proselytize or advertise and explain what's going on here. This paper is, for example, a review of what has happened in my lab recently, catalysis, clean energy, etc. So I recommend you to look at these papers kind of as a roadmap of what we think is one of the most important things. Many other groups around the world doing this, like Tonio Bonassisi and Andy Cooper in the UK, Lee Cronin. So of course, by any means, we are the only ones that are thinking this way. And by mentioning Lee Cronin, I want to move on to a DARPA project that has me very focused. You can notice my fondness of acronyms. The name of this program is called Madness. Lee Cronin came up with that in a brainstorming chat in WhatsApp between the both of us. And what Madness is all about is taking these people that I consider mad, all of us, and think about a diversity or plethora of different automatization platforms to combine with AI models to actually make progress and actually do a self-driving lab for organic electronics materials discovery. So this is really a collaboration of the 5 groups I just showed you before, okay? So I'll be mentioning them as I go along. So why did we pick organic lasers? Organic lasers are the next thing after organic light-emitting diodes, right? Because it will be the coherent version of them. And not surprisingly, Chihaya Adachi has been the pioneer, again, of how to think about them, right? And the way we're going to try to make those organic lasers is going to be focusing on a synthetic scheme that is very similar to the way nature synthesizes its variety of compounds. So if you think about how nature does its job, it actually is using very simple building blocks, iteratively coupling them. Peptides, nucleotides, saccharides, terpenes are all built in this iterative coupling machinery in our bodies. So my friend and collaborator in this project, Marty Burke, was one of the pioneers of thinking about the automation of a single reaction as a potential source of most of the diversity that we need. And the reaction that he identified, by no means a single iterative coupling scheme that we could use, but one that is extremely powerful, is the metaboronate protected Suzuki coupling scheme that you can see here in a series of papers by Marty, allows you to build these molecules that could be either drug-like or materials-like. So we took that to heart and started thinking about how to automate molecules to synthesize them. So we'll come back to it. But another reason why we're very interested in organic lasers is that we can understand their photochemistry, right? We know what are the processes, and here are listed on the left, the photophysical processes that we need to maximize and minimize to make a good laser. And ultimately, what you want is to cycle really quickly and have population inversion over these S1 and S0 levels. So you want to minimize transit absorption, you want to minimize intersystem crossing and then transit absorption from the triplets or non-reactive decay. All of them can be predicted with appropriate quantum chemistry models. So how do we think about robotic synthesis? One of the most important aspects that we think about is we don't want to really enter the retrosynthesis game. We want to use AI for forward synthesis and think about, given a certain number of blocks, say 300, how many molecules could we do with only Suzuki coupling? What are the most varied blocks that we can buy, readily purchasable, that could still give us high yields and create a synthesizable space that we can explore computationally? And notice that if we think our space is 100 million molecules, we're really about 2 orders of magnitude better than what we did in 2016 in terms of molecules that we can explore in my own lab, at least. So to do that, this is where my friend Bartosz Rybowski comes in. He's thinking a lot about forward synthesis prediction, and building AI models that, given the structures of the compounds, predict if the molecule will be reactive or not reactive. Because if we know that there's going to be incompatible groups in this reaction, we're just going to prune our chemical space and not actually calculate that molecule with quantum chemistry, consider it a candidate, etc. So we're going to only explore the synthesizable space by our robots. So this is kind of like the workflow that leads to about 15 experiments per day when we are in full production. I'll tell you where we are right now, of using blocks, shifting down to the chemical space, screening with quantum chemistry to the promising targets, and then using a slow screen, which will be, of course, experimental testing. So this is kind of just telling you there's physical chemistry behind this all. You can do path integral calculations on the electronic structure surfaces to get baryonic results, spectra. The overlap between this absorption and emission spectrum is necessary but not sufficient. Minimizing this overlap is necessary but not sufficient for lasers. And you can predict very well fluorescence lifetimes of certain molecules. And you can, of course, add more and more surfaces and more matrix elements to make this model more successful. But as we do that, we use electronic structure methods, I'm going to skip them, to actually move forward and down select the molecules. Okay, so and the reason I'm skipping is I'm looking at the clock, and I want to be mindful of the time there. So let's come back to the protection idea, okay, and see how it's done in the lab. So you could imagine doing it in several different ways, and I cannot tell you about all of them in this talk, but I have to say we have been successful in several aspects of this in all of the platforms that you see here, in all the different places. Okay, the computer in Glasgow is a fantastic piece of equipment. We just got our first one shipped, both to Vancouver and Toronto. So you can say that you have exported to your former colonies some of your technology from Britain. I bought a ChemSpeed machine from Switzerland, as well performing as a clock from the Swiss. And of course, this is the US-made Illinois machine that we also have one now in my lab as well. So we're really exploring all sorts of different machinery to try to do this. So, for example, in Urbana-Champaign, we have been able to work very well in iterative coupling loops for trying to find out what are the best reaction conditions. We'll come back to reaction conditions in a minute, but what are the best reaction conditions to do this for a generic substrate, but also potentially for specific substrates? So let's just focus on the Toronto robot that we have. We have a ChemSpeed robot coupled to a HPLC mass spec, coupled to lasers, ultra fast time resolved and CW type laser setups to basically measure the molecular properties that we will need to actually quickly screen if a molecule is good or bad for an organic laser. So what is nice about this is that you think about having an organic chemistry lab next to an analytical chemistry lab next to a physical chemistry lab, all in the same room. And that's what really excites me. And what scares me is that they are run by a theoretician. So you can see here the robot in action. This is how it looks. So you can read over there all the different actions, grips, picks up, opens up the drawers, and then it's going to pick up the powder dispensers. And basically that's kind of like the workflow that we're using to, couple, protect, deprotect, and the most important optimizations are how can you use these vials to do the separations for the Suzuki couplings. I'm super excited that one of our first papers from this project is going to be an organic methodology paper to make these Suzuki couplings ChemSpeed friendly. And this is, of course, done by my postdocs and students. I am not a powerful organic chemist, but this gives you an idea of the kinds of things that will matter. From the perspective of a theoretician, this is kind of like a chemical processor that has many variables you can optimize and many different decisions that you could use AI to actually work with. So this is an idea of how our system works. I skipped the HPLC details to just show you examples of real runs where we go out of the synthesizer, HPLC. We use these valves that you see here to separate the molecules and dilute them, and then pump them into our different systems in this optical table to get the time resolved signals and the absorption and emission spectra I just told you about. So now you can imagine this as a fantastic, beautiful playground that can combine the high-throughput screening capabilities that we have on the computational side with experimental capabilities that you see here. So I moved to Toronto in 2018. We started building this. There was a renovation period, an acquisition period. Then COVID came. So it's not an excuse, but we have been a little bit slower than we wanted to finish all of this. So nevertheless, I can report you fantastic progress. This is an example of a run that was happening around last October, where we were trying to couple, for example, 4 boronic acids with 10 metaboronates as a partial synthetic step towards these organic laser materials. This was the success of that particular run. You can see the ones in blue are the ones that got the highest high conversion. You can kind of guesstimate the yields based on the conversion. And you can see the ones that had no product. We did not use machine learning to down select those. This is just a run that didn't filter with machine learning, but gives you an idea that you can actually have some damage. And disclosing to you, super exciting. I'm not showing you the structures yet, but what you see here are molecules that went through the entire process, and they are real laser molecules that are trying to minimize the lifetime of photoluminescence and maximize the relative quantum yield. And some of the optimal molecules are around the circles I show you there. The beautiful picture that you see there in the background there is the actual picture of the vials that came out of this experiment. You can see the colorful nature of them in those particular wavelengths. But this is a real first time that we actually close the loop in an organic laser molecular family. And of course, we're finishing up this work and grading it up, and hopefully it will come out in 2021 in the archive. So it's telling you that, yes, this is a reality. Of course, it's not producing 24/7. There are still experimental issues, and of course, COVID slows us down. So now, in the remaining of this talk, I'm just going to tell you, come back a little bit to machine learning, and then end up with a futuristic agenda. Okay. So what you see here is the ChemOS open source package developed at U of T, and also in collaboration with UBC, Jason Hine, one of the fantastic players in DSO, that basically contains several different aspects, right? Controls the robots, you can chat with it, runs the Bayesian optimization, and has allowed us to do really cool things. But what's under the hood is this series of papers that I'm just going to tell you what they do. You can go and read them for more information. To actually be able to optimize those experimental conditions, or even optimize the set of ligands or categorical choices that you need to do, discrete things, solvent 1, solvent 2, ligand 1, ligand 2, we needed to develop several machine learning algorithms that we call Phoenix, Chimera, and Gryphon. Briefly, Phoenix is one of those traditional Bayesian optimization algorithms that combines exploration and exploitation to try to find out what are the best next experiments to make. Gryphon is crucial because it allows us to relax the discrete variables of combinatorial problems into continuous variables so that they can work together with Phoenix and therefore have continuous and discrete variables treated in the same framework. And Chimera is a decomposer of objectives that is a thresholded multivariable Pareto optimizer that optimizes one variable to a certain threshold and then hops to the surface of the second variable to the second threshold and then to the third one. The human defines this hierarchy and the thresholds, and then we respond with a smoothed surface that allows us to actually give it as an objective function to these optimizers. It is this what's behind the hood of everything that I'm telling you about. And you can actually see it in action and compare to other models by, for example, looking at this Olympus package. Okay, this is a package where you can download the package directly in Python and then compare Phoenix to all sorts of different other optimizers. Okay, and check how well they do in real data sets of chemical experiments that we found in the literature or from our own data sets. So we invite everybody to actually come and look at Olympus, and actually allows us to benchmark your own experiments. Okay, that's really cool. So now let me show you an example, right? So this is an example in production, right? This paper is in the Chem archive, and it's a collaboration with Merck, where Melody Christensen, which is a joint student between at Merck, but with Jason Hine, with my student Flo and former postdoc Loic Roch, coupled ChemOS to an HPLC and a ChemSpeed to try to maximize the yield of this reaction. In this case, we want to maximize the E over Z ratio of this Suzuki coupling by changing the reaction conditions. So you can see here the Suzuki in action. This is the robot at Merck. This is the collection of the data. Okay, this is the Slack interface to ChemOS. You can talk to it in natural language. And then you can actually see the results of about 96 experiments here. This was run twice with different ligands to actually outperform the power of humans. Humans were able to get up to 65% or so E to C ratio over years, but we were able to do it in only 2 experiments by optimizing categorical and continuous variables such as temperature, percentage of palladium, phosphine-palladium ratios. Some of them are continuous, some of them are discrete. And these are different ligands employed for this experiment. So we believe the future is bright for this type of Bayesian optimization algorithms. There was recently a paper by Avi Doyle and my friend Ryan Adams that appeared also on Bayesian optimization recently in Nature. We did this also as well. So we actually put this in the archive before the paper appeared, but who knows what's first, but we are pretty much contemporaries. So now, to come back to physical chemistry and end this talk in basic science, I told you a lot of applied science in some sense, but basic science is super important. There was a beautiful paper by Piotr da Silva that showed that it was possible, perhaps, to have molecules that the triplet was above the singlet. That would be fantastic, right? Because if you have a triplet above the singlet for emitters, that means that you can just relax thermally, right? By intersystem crossing and then fluoresce. Turns out there were molecules discovered since the 70s and so on. The problem is that they were not bright. The emission from the singlet was not really appreciable. So these molecules were dark but had this effect. By using, of course, the techniques that I told you before, mainly here in this particular case, human-driven high-throughput screening, we discovered the first bright molecules in this class. And we call these inverted singlet triplet molecules. That's the name that we gave them. We submitted a paper in the archive. The paper is just now in press, which is fantastic, good news. And it is this beautiful molecular class that we're working together with researchers, some of them in the UK, actually, to actually synthesize and show that these molecules actually exist and matter. And of course, you can imagine that I'm very interested in automating the synthesis of these invest molecules to actually discover as quickly as possible the 5th generation organic emitter. So computer vision plays a role. You can see here our idea of the future automated laboratory, a laboratory where you're actually moving around and grabbing flaskware. This is where a person that you saw briefly earlier today in the dressing room for this talk, actually Nessa Carson, and I understood that she actually was one of the active members of your society. Nessa was one of the contributors of the most images. She turned out to be like a laboratory photo aficionado. So she sent us a huge star file full of images that we employed alongside other images to train this model that was segmented into vessels, materials, and parts, and allows us to take a random YouTube video like this one. And for example, in this video, show you what we consider is actually a solid. There's no solids. What we consider is a liquid, and we consider is a vessel. Okay? So you can imagine this is going to be the eyes for the Terminator robot of the future that will actually do chemistry in the laboratory. So we're pretty excited about this, and now we're working with robotic arms to actually make the first robots that actually do this with computer vision in an unsupervised kind of table. So this is kind of where I think my lab is going to be going. And on that note, I'm just going to end by really thanking my group members. This is the Zoom version of the photo of them. I really just can't wait to go back to the lab. And also, I am sad that I'm not there to talk to you guys and then drink in the beautiful Harry Potter room that I've been there before. Somebody asked me in Twitter to make Harry Potter jokes to you guys. So on that note, I'm going to end and actually have some questions and answers if the time permits. Thank you very much for your online attention.
Thank you so much for the talk. It was really interesting, and we have many questions. So Lorenzo, keep them coming. There you go. We have the first one. It comes from Karim Thomas, and he's asking, what other family of materials besides OLEDs do you envisage as low-hanging fruits for this kind of platform?
Hi, Karam. Nice to see you here. I think we are focused, and there's all sorts of classes of materials, but we are focused on small molecule materials where the small molecule has the main role. So you can imagine this being very useful for pigments that you can imagine embedding in medical plastics. You can imagine this being very useful for electrochromic molecules, as our startup company Robotics has shown. You can also imagine this being very useful for organic flow battery molecules. We're working on that, including its automation, etc. So that's what I focus on. But we're also building a catalysis robot together with the Natural Research Council of Canada. So you can imagine doing this for solids and for all sorts of other applications.
Sorry, I was muted. We really have a very broad range of applications for this sort of technology. So we can go all the way from like light-emitting materials to catalysis, touching all of sort of the ranges of materials science. So it's really cool. Can we have any? Oh yeah, sorry.
Go ahead.
So I saw there was a very related question in the chat. So Lorenzo, oh, there you are. So Nessa is asking us about the data for reaction optimization. So this data is essentially very variable. So how can we optimize it? Or how can we make optimization of the variables if we have such a noisy input?
Fantastic, Nessa. So first of all, you could imagine doing reactions multiple times to get a distribution of your errors. So as you know, sometimes there's even robotic errors, right, that you have to deal with. You probably know this very well. The other strategy is obviously the models that we use can also assign an uncertainty to each data point. So you can also, if you know an idea of how uncertain is a data point, it can also go back into the optimizer. So this could be some of the strategies to deal with it. But also, we are working on robust optimizers that think about the noise aspect. We have one that, for example, is trying to optimize for mesas rather than peaks. We call it Golem, and it was inspired by our conversations with Merck. So there are algorithms that we're developing exactly to tackle this type of questions.
That's wonderful. So I assume there's a lot of work beyond sort of off-the-shelf solutions for optimization for this kind of problems.
Sorry, Carlos, I kind of missed you for a second. Can you repeat
sorry.
the question?
Yes, no. So I was just commenting on that. So there is a lot of work beyond sort of naive off-the-shelf optimization algorithms. So you've had to do your group has had to do a lot of work to find algorithms that are robust to the sort of problems in experimental chemistry.
That's correct.
Okay. Actually, we have a follow-up question from Nessa. Let's move to this one then. So Vlad is asking, knowing probably that you are also an important researcher in quantum computing, do you envision quantum computers will have an impact in this field in the future, and to what extent?
Hi, Vlad. So it's funny, right? You know, half of my group does quantum computing. I didn't mention it at all in this talk. And half of my group does this. So for those of you that are looking for postdocs, this is a great, or grad students, this is a great place because you learn from both sides. I started 2 companies. One of them is called Robotics, that works in this space. And one of them is called Zapata, that works in quantum computing. I sometimes joke for the moment where they will merge, or one buys the other. And then all my worlds join. When will that happen? When quantum computers are able to do exact predictions for molecules that matter of this size. This could happen in the next few years. Depends on the experimental progress in the quantum computers and the algorithmic progress. If I were giving to you a quantum computing talk, I would have told you how rapidly the roadmaps of companies like IBM and others are going in terms of number of qubits, and how much progress we are making in the algorithmic side to reduce the requirements. It is just a question when the two are going to meet. We don't know exactly when that will happen in the future. That will be for very small molecules. Then we have to wait until it scales up, okay? And then I think when this is going to be integrated in a full production for molecular simulation for real, I don't know. I'm not going to give you a number, but of course it's years away, but not as many as you think. I'm not going to give a number publicly, but I don't think it's impossible that a quantum computer will be entering this kind of discussion within the next decade, let's say. And then, you know, I would love to be giving back this talk in Oxford a little bit older.
That's wonderful. Maybe Keolux will buy, maybe Robotics will also buy Keolux, and then Zapata, and then all of your startups will join into one big startup to rule them all.
Yeah, bring it on, Elon Musk, you know? Yeah.
Can we have the next question, Lorenzo? Okay, this is a follow-up question from Nessa. She's saying some reactions and some conditions are very uncommon, and humans are biased because we use the same ligands for cases where they work. So she's still worried that algorithms will not work well in these islands of missing data. And there's a bit that is missed in the question, which says, will this be okay?
Well, Nessa, this is the way I think about this. Just give the field time. We need to become the masters of Suzuki, Buchwald-Hartwig, simple reactions like that. This is where the field is, right? We want to make sure that our AI or computational chemistry are out there for the reactions that are the most diverse in terms of substrates and scope, at the same time the most useful. Carbon-carbon couplings, for example, carbon-nitrogen couplings, things like that. And again, I'm not an organic chemist. Now, if you go to these esoteric reactions where you have very little data, paradoxically, I argue that's where machine learning might be the biggest impact, okay? Because it will be exploring the space faster and more intelligently than a human in the following sense. As you're maximizing your return and saying, this is a place where I need to do the next experiment to gain the maximum amount of information, you might minimize the number of experiments necessary to optimize such a reaction. If there is no data after all, you might as well generate it smartly. So the question is, I think, if there's a space with little islands of data, what is better, putting a robot to explore and pick those data points and optimize, or a human? And maybe this is a good experiment that could be like a CASP type competition, right? Give a new reaction that has not been discovered, and then have everybody throw the robots or the humans at it and see who wins. Maybe that's a good experiment, right? And then you can use as much human knowledge as you want too, right? Or literature researches or whatever. It should be a fair game.
Wonderful. So we are close to 1 hour. So let's take 1 or 2 more questions and then we'll finish. If that's okay. So Lorenzo, go ahead. Right. Oh, I think it's a really interesting one. So you said that the probability distribution of images is very complicated when you were talking about the images. How does the probability distribution of materials look like?
That's a very good question, whoever asked it. In the papers, if you go to the papers we have published, we spend a lot of time thinking about what is the structure inside of the latent space. I didn't show here your slides, but we have experiments where we sit down on a molecule and explore the space around it and see how different are the molecules represented around that space, right? We have also done many experiments where you take molecule A and molecule B and interpolate between them and see what is in the latent space along the way. And as I showed you an example with stoned, we can even try to optimize for a property as we're doing that and try to find a molecule that satisfies, say, 2 receptors. So we look a lot there, but we're looking at it more like statistical explorers. But we're trying to see what did the machine learn and how is that space structured. And for that, that's where the deep dreaming comes in. We can enter the neural network from behind, so to speak, and figure out what's happening, as I showed you very earlier in this log-P experiment, for which, by the way, I just saw the data this morning. This morning, I was looking for updating my talks because I gave 2 talks today. And I see in my Slack, this guy's telling me, oh, Cynthia, which, by the way, is an undergrad, sends me this plot that I just showed today that was needed for submitting the paper to the journal. We really wanted to have this interpretability section. So it came this morning. So it's so new, right? But we're getting into the direction of what the heck did the neural network learn? And this is a huge problem in machine learning that everybody's tackling, and we're just trying to do the chemical version of it. But what I mean by complex is, it's not obvious, right? If I give you the distribution of the smiles of all the drug-like molecules, and I ask you, produce me a smiles of a drug-like molecule, how do you start? The fact that these neural network models, like the autoencoder, are able to do that, I think has been revolutionary, and I'm not exaggerating. That is like a new area of theoretical chemistry.
Wonderful. Well, I think this is a super interesting question. As in, what does it actually look like, right? It's like a discrete space where you can have all sorts of changes. So I think it's a really cool question. And I think we have time for one last one. So Lorenzo. Okay. So this is a wonderful question to end. So what are the upcoming advancements in machine learning for life sciences and organic chemistry that excite you?
Well, thank you for the question, whoever asked it. it would be good, guys. It's a recommendation for your society. If, like in the case of Nessa, you actually put who was the person. Maybe this is anonymous, but it's kind of nice because sometimes there are people that you know, like Karam or Nessa. And anyway, this is just a suggestion for the next one. But just to end in time, and because I know it's late over there, let me give you my philosophical answer to this. We're running a paper with Mario Kren, several other group members, CEO Guo, Robert Police, and many, many others. And this paper has taken us a long time because we're trying to think about what's next, right? What's next? Because you see, after all this data science I told you about, it's about the model and the representation. But what we really are about is about computers discovering new things. So for that, we're going back to other forms of AI that are more symbolic in nature to actually embed concepts, to be able to say that the machine learning is giving you back conceptual relationships, right? There is a beautiful paper coming out of the UK very early on Adam, the first self-driving lab I know about, okay? And Adam is a robot that is basically taking the gene expression network of yeast and eliminating genes to see what happens, and then trying to infer what exactly is the gene expression network. Okay, that's called abduction instead of induction, right? By removing elements. So this thinking in counterfactuals and things like that is what makes us human. And the question of how we can actually use AI to do that is one of the questions. Another thing that really excites me now is robotics. What is the frontier for a robot to do chemistry freely? I think ultimately maybe that's going to be the platform that's going to win.
So you think the future is neurosymbolic AI and things in this area?
Neurosymbolic AI, basically on top of that, connected to a robot that is walking around in the lab and is grabbing flasks that are. So you tell the robot, go find this powder, and goes and opens the drawer and like starts looking at the flasks one by one and like says, here it is, right? And it's talking to you and coexisting with you in the lab. It is this future where suddenly there is a robotic scientist next to us that excites me at the moment. But ultimately, remember, let's go back to the first question. Why are we doing this? I am 44, people. You guys, many of the listeners are younger than me, maybe in your 30s and your 20s. We are the generation that needs to use science to save the freaking planet. It's not, other generations didn't have this problem. So remember the motivation. The motivation is to accelerate the discovery of materials. I recommend you in all your different scientific disciplines, think about both the two aspects, the basic aspect, but also the applied one, where you actually can potentially contribute to society, because unlike other centuries, I argue this one is very special. Time is running out. We need to do things like, for example, discovering a COVID vaccine in a year. Think about this is almost as going to the moon, to me, the Moderna and Pfizer mRNA vaccine story, right? Can we do this for materials? Can we do this for other areas in humanity? I think this is going to be the type of science that I want to see happening more and more.
Well, this was a great point to end this lecture on. So I don't know about you, but I'm really, really excited about these possibilities. But I'm afraid that we don't have any more time for questions. So first of all, many thanks to all of you, our audience, because we wouldn't be here without you. And special thanks to our AV officer, Lorenzo, who's always behind the scenes, making everything work smoothly. And of course, I hope you will join me in thanking Professor Aspuru-Guzik for taking time out of his busy schedule. I think this is the second talk that he gives today, probably the fourth that he gives this week. And I just want to take this time to advertise next week's talks. So we have not one, but two. One on Monday from Dr. David Lung from Entrepreneur First, who's going to talk about why you should become an academic entrepreneur. Alán probably can tell us a lot about this. And another one on Thursday from Dr. Patricia Farah, who will talk about the life of Isaac Newton and the history of the discovery of gravity. That's all for us. I hope you enjoy the rest of your evening, and hopefully see you next week.